Hey everybody, it's time for another rip-roaring and thrilling edition of Unit 6 on rational and radical expressions. What we're going to transition into now is actually making that subtle shift of another way that we can write radical expressions, and we can actually write radical expressions using exponents, believe it or not. To put it to you this simply as I can, let's go to the graphing calculator right now. Here's something that we know for a fact, right? If I ask you to take the square root of 64, we all know what the answer of that is, correct? That would be 8. Okay? Did you know that you can actually take 64 and raise it to a particular power? And when you raise that to a power, you'd still get 8. Any ideas what number that would be? If you're not sure about what kind of numbers it could be, well, let's first rule out some numbers. First off, can we rule out any positive numbers? No matter what positive number we pick, there's no way that this would work. Oh, I don't know why that turned out to be exponent of 2. How about I do this? There we go. Realize that with any positive number just gets larger, right? We take 64, raise it to the first power. That's no good, stays 64. I want it to go down to 8. So then the next logical choice, how about taking 64? Let's raise it to some negative numbers. What happens if you take 64 and say, I don't know, let's raise it to the negative second power. Be careful how I write that negative. And we're expecting 8, right? That definitely does not look like 8. In fact, if I were to fraction that guy out, kind of looks like, I don't know, looks like 1 over 64 squared. So interesting, that's not working either. If we try 64, hey, there's actually a dedicated inverse button right there. Does that work? So I guess, no. In fact, I think that would just get us 1 over 64, wouldn't it? Yep. So, what kind of numbers have we left out here? Well, you take 64. The only other number I could think of that we left out so far would be 0. Anything to the 0 power would give you 1. I'm looking for 8. Let's see here. What happens if I take 64 and raise it to a square root? Let's try 1/2 and see what happens. Oh, look, there's an 8. Interesting. So 64 to the 1/2 power is essentially the same as taking the square root of 64. I think 64 is a special case. Does this work with all perfect squares? Or in fact, does it work with all radicals? Absolutely it does. Okay, even non-perfect squares. If I take the square root of, say, 7, I get a really weird decimal. But if I take 7, raise it to the 1/2 power, I should get that same irrational number, which I do. Okay, so that's rule number 1 here, is that we can take radicals, like square roots, and we can rewrite them using exponents. So that's the first essential understanding right here, is that any nth root that you see right here can be written as 1 over n for any positive integer n. So if I want to take a square root, that would be 36 to the 1/2. If I want to do a cube root, it'd be 64 to the 1/3. If I want to do a 4th root of 16, it'd be 16 to the 1/4. And so there you have a couple of examples right down here. If I want to take 216 and raise it to the 1/3 power, that is essentially the same as us taking the cubed root of 216. Cube root of 216, calculator can get you down to there, that's 6. I don't need to see this move right here in the middle of you writing it as a cube root of something being raised to a cube. Same deal here. Look what happens on this situation. 7 to the 1/2 times 7 to the 1/2. Isn't that really saying the square root of 7 times the square root of 7? Because it's a 1/2 power. So square root of 7 times the square root of 7, we multiply those together, and then sure enough we get the square root of 49, which is absent here, but I can see why they went and did it this way. The square root of 49 would just get us down to 7 right there. And then take a look at what they end up doing here. A 4th root of 5, not 4th root, yeah, it actually is the 4th root of 5, I just was getting ahead of myself there, but 5 to the 1/4 times 125 to the 1/4, it's 4th roots of 5 times 4th roots of 125. Since they both have a 4th root, it's actually okay to multiply those two numbers together, get 625, and I need to try and figure out a number that when I multiply it by itself 4 times, I get 625, and that answer would be 5. Remember, you can actually use calculators to help you with that, right? If I want to do a 4th root, hit 4, math, number 5 right there. So now it's taking a 4th root of 625, and there it is. There's that 5 right there. Okay? So now it's your turn. Let's take a look at this. Go ahead and give that a pause, and then see if you can simplify each one of those 3 expressions. Okay? And we'll come back here in a little bit if you have not already paused it. Alright, so if you've paused it by now, let's take a look at some of these answers. Let's check your work. Alright, so the first one is square root. Well, kind of gave it away. 64 to the 1/2 power is no different than us saying the square root of 64. Right? It's like having a little 2 right there. And then I do not want you to leave it like that. If the square root is an integer, I am expecting you to go even further and tell me that the answer is 8. Okay? We look at B. We have 11 to the 1/2 power times 11 to the 1/2 power. Wouldn't that be the square root of 11 times square root of 11? Which would be the square root of 121, or the square root of 11 squared, which would just end up being 11. I'm going to come back to that one here in a minute. And then if we look at this next one here, even though they don't have the same base, we can still rewrite each one of these. That's the square root of 3 times the square root of 12. Since they are both square roots, do you notice it's okay to multiply the 3 and the 12 together? And we have the square root of 36. Hey, wait a second. I think we can take the square root of 36, and we end up getting 6. Now, the nice thing about doing this way and thinking that maybe we may have made a mathematical mistake here and saying, maybe we broke some rules. Because, Mr. Cook, I remember you telling me some rules like something like this. The square root of 2 plus the square root of 3, that's not equal to the square root of 5, right? And so, am I breaking any rules here? It looks like this is almost too easy, right? Remember, you have a graphing calculator. You can check your work here. If I have 3 to the 1/2 power times 12 to the 1/2 power, according to this work, my answer is 6. So let's go ahead and check our work. Let's take 3 and raise it to the 1/2 power. Instead of putting it as a fraction, I'll just put it as a decimal. And then let's multiply that by 12, and let's raise that to the 1/2 power, which would be 0.5. And if I really did this work properly, I should get 6, right? And sure enough, boom, there's 6. So my math is legit. Now, I want to go back to this problem over here. This B, and even this B right here. Could you figure out another way out of this mess rather than actually rewriting these as square roots? And think about some of your previous algebra work when it came to properties where you have the same base and what you can actually do to the exponents. That's right. Isn't another way of saying 11 to the 1/2 times 11 to the 1/2 exactly the same as saying 11 to the, let's see here, 1/2 plus 1/2, right? We can add those exponents up, which would be 11 to the 1st power, and last time I checked, 11 to the 1st power would be 11. Do you notice we could have done the same thing right here? 7 to the 1/2 times 7 to the 1/2 would have been 7 to the 1st, which would have ended up being 7 right there. All right, so that's how these problems end up working here. So you'll see a couple of these problems should be quick work. Remember, I want the most simplified answer. So if you have a square root and it is a perfect square, or if you have, like in this middle case right here, a square root but also a square that would undo each other because of inverse operations, I do want you to give me the simplified answer. All right, let's move on to problem 2.